Let's go over the torque practice problems that you guys did the other night. Let's start with the bottle on the rod. We have a weight and we're going to rotate it. When it's vertical, my hand produces no torque about that rod. As I start to lift the end of the rod and I rotate it, yeah, I can actually feel this. This is the first demo in my chapter notes. You can see it for yourself if you look at the notes. And this is something that you can easily set up at home. Do not put a lot of water in that bottle. You don't need a lot of weight to feel this. Now, what is actually going on here is this is an emphasis on the idea that torque is a force times a distance from a pivot. Now, where exactly is this pivot? It's in my hand somewhere. Let's get a closer analysis on that. If I simplify this, you can see that I could make this the pivot and make my heel of my hand pushing down, which produces a counterclockwise torque, and the bottle on the other end is going down, producing a clockwise torque. So I could make that the pivot if I want to. On the other hand, I could think of this as the pivot right here. That means my finger is pushing up and the bottle is pushing down. This creates the counterclockwise torque to stop the clockwise torque. Now, this is the position where you will have the most torque. You can feel it for yourself if you just simply hold the rod and start lifting. The further out that bottle is from the pivot, the greater the distance, the greater the torque. When it's vertical, there's a force, and you might say, hey, there's a distance. But the distance and the force are parallel. They're not perpendicular to each other. So remember this now. If the force goes through the pivot, you're not going to produce any torque. And now for a seesaw problem. But first, we're going to take a look at the center of mass of the meter stick. The center of mass turned out to be in the middle. And that's because the stick was uniform in density. One side is not heavier than the other. This equipment is very sensitive. Just move the center of mass away from the pivot and it will produce torque. Here we've moved the center of mass only 1 centimeter away from the pivot, and it produced plenty of torque to make this thing tilt. So remember, if the center of mass is right under the pivot, it won't produce any torque. Now, what did we discover when we put weights on here? We found out that if one weight was twice as heavy as another weight, it ended up being half the distance from the pivot. We measure all the distances from the pivot to the force. We also realized that the force is perpendicular to the distance. The force missed the pivot, causing a clockwise rotation. This force missed the pivot, causing a counterclockwise rotation. And of course, we tried this with different combinations and discovered the relationship remained the same. A comment about the equipment is that this is much better than the stuff we have at school, actually. You can change the amount of weight you have in here, and you have your electronic balance so that you can check it out and get everything perfect. And it's quite stable. It doesn't fall off and go all over the place. So here's our seesaw lab, and we'll do the math now. You have to label your diagrams. We found that D1 goes from the pivot out to the force, and so does D2. This force was 1.4 newtons, and this one was 0.7. And it works out perfectly. That's 20 centimeters, and that was 40 centimeters on the experiment. On the Google spreadsheet, people discovered that F1D1 equals F2T2, and all the data is bearing that out. I told you that that was called a torque. And that sometimes we put the perpendicular sign in there to make sure everybody realizes the force and the distances are perpendicular to each other. One's counterclockwise, the other one's clockwise, and they balance out. We can see that it worked out to be 28 Newton centimeters. Those are the units for torque. And on the other side, we also have 28 Newton centimeters. Well, if you think of one as being positive and one as being negative, we can say, well, if we add them up, they add up to 0. We say the system is in rotational equilibrium. It's not rotating, but don't forget, it's not going up or down either. So we say the sum of the forces is 0, and the system is in translational equilibrium. And these are the conditions for the translational and rotational statics. Let's take a look at this last idea. These forces are going down. Well, then what must that pivot do to the meter stick to keep the whole thing from falling? It will push on the meter stick with 2.1 newtons up. But what if we include the weight of the meter stick? It's 0.5 newtons. That number now has to be 2.6 newtons to stop it from falling. But what about the weight of the meter stick producing torque? We never saw that in the calculation because the weight of the meter stick went right through the pivot in this example. A word of caution is in order. I asked, what does the pivot have to do to the meter stick? That's got to push up. But what if we said, what is the meter stick doing to the pivot? It's pushing down on the pivot. You got to be careful about the wording. In the next part of the lab, we added a third weight to the right side. Hey, it went down. I moved the bag of beans in a little bit and it all balances. Now I draw a new diagram. I put the bottle on the scale and I got 21.8 grams, and we're just going to approximate that to be 0.218 newtons. D1 is 40 centimeters, D2 is 14, and D3 is 38.6 centimeters. Again, we start right off with torque counterclockwise equals torque clockwise because we saw that it's balanced about that pivot. Some of you in lab figured that it would make sense to put an F3 times a D3 on this side because that force will cause the stick to rotate clockwise. Plugging in all the data, of course, we still get 28 Newton centimeters on the left side. And look at that, we get 28.015 Newton centimeters on the right side. So let's try this problem. What if you had a meter stick? I told you everything was balanced. You've got 5 newtons on this side at 10 centimeters. You have 3 newtons all the way out at the end. The weight of the meter stick is 2 newtons. And now you have to figure out where this 4 Newton weight would go to make it balanced. You should start with torque counterclockwise equals torque clockwise. And now pause the video and go try to solve the problem. So here we go. How did I have 5 newtons times 40 centimeters? That says 10 centimeters. Well, that's the meter stick, and it's measured from the left end. But the pivot we've placed is here, and there's 50 centimeters. So how far is this force from the pivot? It's 40 centimeters. That's why we put that there. Filling in the rest of the data similarly, we get 12.5 centimeters for D3. But the question is, where would we put it? Well, you have to understand what that means. You would want to put it on the side to make it go clockwise, and that's 12.5 centimeters from the pivot, which would be at 62.5 centimeters. What if the question was, what's the torque counterclockwise? You'd have to say 200 Newton centimeters. A torque is not a force. You have to multiply it by the distance to get the torque. Another question could have been, find the missing torque. If we know on this side we have 200 Newton centimeters, and on that side from the 3 newtons we have 150 Newton centimeters, then obviously the missing torque would be 50 Newton centimeters clockwise. And of course we can ask, what does the pivot have to do to hold this meter stick up? Yep, it'll have to push up with 14 newtons. Now we set the meter stick up with no weight on one side, and we have to find the weight of the meter stick. We have the pivot at 20 and the weight at 11.8. The bag of beans weighs 1.4 newtons and it's at 11.8 centimeters. The pivot's at 20 centimeters. Where's the weight of the meter stick go? At 50 centimeters. We already figured that out. Again, it's torque counterclockwise equals torque clockwise. Did you figure out that it would be 8.2 centimeters? That's the distance from the pivot out to the force. And out to the weight of the meter stick, 30 centimeters. And we get 0.383 newtons. All right, not bad. It could be closer. Well, that's the theoretical. And here's my experimental. And that's about a 13% error. Yeah, in the actual lab you did better than me. I just went back and checked that number. It actually is a little higher than that. So that would have brought it a little closer. But if you're careful, this works out really well. Now, what does the pivot have to do? The pivot must push up with 1.8 newtons. Before we move on, let's look at the same situation and ask, where's the center of mass? It's got to be right over the pivot. If the center of mass was to this side of the pivot, it would be rotating this way. If the center of mass was to this side of the pivot, it would be rotating the other way. The center of mass has to be right over the pivot, and there's no torque produced by the center of mass in that situation. So let's look at the center of mass for this situation. We'll ignore the weight of the meter stick. 5 newtons on one end, 6 newtons on the other. Another way of saying where's the center of mass then would be to say, where would you put a pivot to make it balance? Now, we've seen this in class. Here's the demo you did at home. You took the clamp, put it on the end of the meter stick, and then you found the center of mass by trying to get it to balance. And you found out that the pivot has to be closer to the heavy end to cancel out the torques. But we don't know exactly where to put the pivot, so we just generalize it and call this side X, which would automatically make that side 100 centimeters minus X. Now pause the video and solve it for yourself. You're going to say the torque counterclockwise is the 5 newtons times X. The torque clockwise is going to be the 6 newtons times 100 minus X. You do all the algebra and you get 54.5 centimeters. Since X represents the distance on the left side, yeah, we would put the pivot at the 54.5 centimeter mark. Let's try an alternate solution. Same diagram, same weights, we'll still label that X, but I'm going to ask you, what does the pivot have to do to push up so the whole thing doesn't fall down? That's actually useful information. We're going to make the left end the pivot, just mathematically. The torque clockwise will be produced by the 6 Newton force times that distance from this pivot. The counterclockwise torque will be produced by the support pushing this way, that's 11 newtons, times X. Clockwise torque, counterclockwise torque. What about that force? If we call that the pivot, it produces no torque and it doesn't appear in the equation. We still get the same answer, and I'm telling you, the math is easier. All right, we're going to change the numbers this time and make the weight of the meter stick 2 newtons. How are you going to solve that problem? You could ask yourself, where would you put your finger to make it balance? That's how we find the center of mass. Again, pause the video now and try to solve the problem. First thing I'll do is I'll label the weight of the meter stick 2 newtons right in the middle. You would put your finger closer to the heavy end to make it balance. How hard would that have to push up? 19 newtons. We don't know where it is exactly, so we will call it X. That would be the distance to the center of mass. Again, start out with torque counterclockwise equals torque clockwise, but to make the math easier, we'll measure all the distances from the left end, pretending that's the pivot. If you don't do that, you're going to have X, you're going to have 100 minus X, and then you still have to deal with this. So there's another thing there with a minus X in there. It's too complicated. The 5 Newton force is producing a clockwise torque about that pivot. It's 100 centimeters from the pivot. The weight of the meter stick also produces clockwise torque about that pivot, and it's 50 centimeters from the pivot. That's where the center of mass is of just the meter stick. Well, your finger pushing up, going counterclockwise about that pivot, and we're going to call this 19 newtons times X, and that's the distance to the center of mass. And we get 31.6 centimeters. Makes sense. That's closer to the heavy end. Now keep in mind, that is not an extra pivot that we put there. It's just a dot to set up the math. Now I'm going to show you the same problem, but drawn a different way, and you don't recognize it. What if I had a 12 Newton weight attached to a lightweight stick? with a 2 Newton weight, another lightweight stick, and a 5 Newton weight. Both sticks are 50 centimeters. If I ask you to find the center of mass, many of you say, I don't know how to do that problem. It is this problem. You call the left end the pivot. You imagine putting your finger somewhere along here, closer to the heavy end. You know that that finger would have to push up with 19 newtons, and the distance would be the unknown distance to the center of mass. That's where the center of mass is. So in terms of the distance along the x-axis to find the center of mass, it doesn't matter if these weights are attached to the meter stick here or hanging by a long string. We're only looking at the x positions. One more question about the center of mass. Imagine I have 10 Newton weight and a 5 Newton weight on a lightweight stick. The center of mass would be closer to the heavy end. Now imagine I just throw this into the air and give it a spin. What's it going to look like? While it rises and falls, it's going to be rotating about the center of mass. Now I showed you that on a video of me throwing a lab stool. It turns out you don't have to have any mass at the center of mass, but it's a point about which everything will rotate. Now we move on to the bridge crusher problem. We'll ignore the weight of the horizontal beam. We've built bridges, we put weights in the bucket, and we crush the bridges to see how strong they are. I think you can see that the weight of the bucket will make the rod rotate in a clockwise direction, crushing the bridge. Well, what does the bridge do to stop this bar from rotating? The bridge will have to push up on that bar. So these are the forces that we're interested in applied to the bar. Where's the pivot so we can set up our torque equations? It's on the left end. There really is a hole drilled in this thing with a bolt going through it to make the rod rotate up or down. So we can say the weight of the bucket times 80 centimeters, the distance from the pivot out to the force, is equal to the force that the bridge must exert times 20 centimeters, that distance out to the force. Let's say we make this bucket 100 newtons. Now the bridge is exerting 400 newtons up. But what does the bridge crusher do to the bridge? It has to push 400 newtons down on the bridge. So again, the wording can be tricky. Read it carefully. Well, I'm looking at this horizontal beam, and I'm going to ask you, what does this pivot have to do to that beam? If the bucket has 100 newtons in it, and the bridge is pushing up with 400, well, they're not going to cancel out. If we say the force is up equal the force is down, obviously something's missing. You need to put the force of the pivot on this side. It's 300 newtons. In the diagram, you can see it's got to be down. 300 down, 100 down equals 400 up. Now, what if you didn't have more than 100 newtons, but the bridge wouldn't break yet? What could I do with that bridge to try to break it? Move it to the right or move it to the left? The clockwise torque is set. It's 100 newtons times 80 centimeters. But that force of the bridge will change depending on where we put the bridge. If I make D smaller, this will get bigger. That means moving the bridge closer to the pivot. And now we have our truss lab with torque. In the original truss lab we did, we had the weight all the way out on the end, and all the forces went through one point. But in this lab, we move the weight in, and now we're not really sure how much of that weight is on this side, how much of that weight is on that side. So what we do is we use torque. And here we have the truss setup that you built at home. We're using the door as the pivot. This weight going down produces clockwise torque. What's producing the counterclockwise torque? Everybody says it's the string, but actually it's just the Y component of that string. The force of this string can be broken up into two components, a vertical and a horizontal. That X component is going through the pivot. It's not going to produce any torque. Let's do the math. We have a 1.4 newtons at about 60 centimeters. The string is really attached somewhere around 98 centimeters at the top there. And using the protractor, I get about 32 degrees. So here's the data on the diagram. The meter stick weighs about 0.4 newtons at 50 centimeters. The weight of that bag was about 1.4 newtons at 60 centimeters, and we have the angle at 32. I'll say torque counterclockwise equals torque clockwise. Our goal is to solve for the force of that spring scale. Why don't you pause the video now and see if you can do it? The clockwise torque is going to be produced by the 1.4 newtons times 60 centimeters plus the weight of the meter stick times 50 centimeters. What's going to produce the counterclockwise torque? Well, the force of the scale is going to have a y component and an x component. The x component can't help us because it's pushing through the pivot, producing no torque. That is perpendicular to this distance, and that's what's producing the torque. I'm using 98 centimeters because that's about where that string was attached to the top of the meter stick. My y component is 1.06 newtons. Is that the answer? Is that what the scale reads? No. It's 1.06 newtons for the y component. How do we get the force reading of the scale? We're going to have to take this vector and imagine it is opposite the 32 degrees. We could put it over here. We have a right triangle. It's the same old vectors we've been doing since the beginning of the year. And that's what the scale reads. Let's go find out. Hey, right on the money. Now we can ask ourselves, what's the pivot doing to the meter stick? The x component of that string is pushing the meter stick to the left. Something has to stop that meter stick from moving to the left. Yeah, it's the door pushing to the right. And the weight of the meter stick is going down. What's stopping the meter stick from falling? That block of wood. So the pivot, let's assume, is the corner. It's pushing up and to the right. Well, let's take a look at the forces up and the forces down. Forces up, forces down, they don't cancel. The pivot must act up. We put it on this side of the equation, and we get 0.74 newtons. Now, what about the forces going to the right versus the forces going to the left? Well, we have an x component here, and we don't know what it is yet. You take the cosine of the angle times the force of the scale, and we can say that the string is pushing the meter stick to the left with 1.7 newtons. What's the pivot have to do? It's got to stop that meter stick from moving to the left. It has to push to the right with 1.7 newtons. Now we can say the sum of the forces is 0 as well. Now we've left the pivot force in x and y components, but we could always put those together and calculate the resultant of the pivot force. Now I know there's more problems than just these, and there's all sorts of variations on these. You'll find them in the chapter notes. The typed up torque examples that are in the PDF that we sent you. And we have Word document worksheets that were sent out as well. Watch the videos. Do all the labs. Use that lab equipment to prove what we're talking about. Well, I have to make a comment about people telling me that they're still adjusting to the online learning. Well, I want to tell you that if we were in school, you wouldn't have had lab equipment at home to do everything. You'd be probably sitting at a lab table watching others do the labs. There's no videos. There were no videos when everybody was back in school. You can watch a video and learn something at midnight. How many people have Zoomed with me at 10 o'clock on a Saturday night? There was none of that before. You had to stay after school. A lot of kids couldn't stay after school. The biggest factor in your success is going to be doing physics every day. It's your motivation that's extremely important here. You can't wait until a few days go by and then try to bang it all out. We don't learn physics well that way. And when we have a quiz in school, you want to know what hard is? You don't get to use your notes. And for years, I've heard people say, I understand everything. I just can't do the quizzes. Well, this is how we find out if you understand everything. If you can't do these quizzes, believe me, there are things you don't understand. Now, I understand that there's pressure, and some people just get confused under that pressure. But that doesn't explain why you can't get better than a 50 on these things. That's not possible. There's a lot of things that you don't understand if you're not doing reasonably well on these quizzes. So how do you study? Of course, we have to practice the problems. I've got lots of examples. People look at them and they say, oh, what's D2? Oh, I follow that. Goodman put down 25 centimeters. Well, that's not the way you study. You have to cover everything up, work it out, and then check your work. Too many people look at what I've done and say, oh, I follow what he's doing. Oh, see, I understand everything. It's not the same as doing it on your own. And lastly, let's talk about timing. People run out of time on a quiz. You're going to run out of time on the SAT test too. And what do they tell you? Skip the hard ones, go on to the more easy ones, because you're going to run out of time and then you're not going to be able to get points for the easy ones.